Our project focuses on the hardness of decoding linear codes. Our video will describe the hardness of decoding linear codes through using a proof in 1 to prove that the problem is NP-complete. The video will also give an application of this problem to cryptography. We recommend that viewers have a background in basic linear algebra, coding theory, and some complexity theory. The problem that we will be discussing in this video is the general hardness of decoding linear codes over F2. It is well known that this is hard, and is specifically proved in 1 that the following decision problem, termed the maximum likelihood decoding problem, is NP-complete. Our input is a binary matrix H in F2 with dimensions m minus k cross n, a binary vector y in F2m, and a non-negative integer w. Our question is there a vector x in F2n of Hamming weight less than or equal to w such that hx transpose equals y transpose? Our solution breakdown is as follows. First, we will be giving a proof of the NP completeness of MLD from our first reference. The proof involves reduction from the three-dimensional matching problem. First, we prove that MLD is in NP, and then we reduce the three-dimensional matching problem to MLD. The NP hardness strongly suggests that there is no polynomial time algorithm that will solve the general decoding problem, and the general problem of finding the weights of linear codes makes the Michelese cryptosystem an important system in the survival of cryptography. Why is this problem interesting per se? Well, our linear codes allow for efficient representation. The fact that the maximum likelihood decoding for general linear codes is hard is then sufficiently non-trivial when viewed through this context. In addition, the proof technique used to give the reduction involves a three-dimensional matching problem that is different from the usual three-sat problem, which makes it interesting from a complexity point of view. The motivation behind the application to cryptography is that the Michelese cryptosystem cannot easily be broken by quantum computers because of the use of general coding theory, GOPA codes, in the encryption-decryption process. The strongest known attack is based on solving the NP-hard decoding problem, and no quantum algorithm has been proposed, which increases the efficiency of this attack.
I'll quickly review some basic definitions from complexity theory. We say that a problem X is reducible to Y if arbitrary instances of problem X can be solved using a polynomial number of standard computational steps plus a polynomial number of calls to a black box that solves problem Y. Note that this is a transitive property, as X is reducible to Y and Y is reducible to Z implies that X is reducible to Z. Similarly, we define NP to be the class of problems that can be verified in polynomial time. Now, if for all problems Y in NP, Y is reducible to X, then X is said to be NP hard. That is, all the problems in NP can be solved in polynomial time using a black box algorithm that solves X. Finally, a problem is NP-complete if it's in NP and is also NP-hard. Recall that our goal was to prove that the maximum likelihood problem MLT is NP-complete. Let's first formally define the maximum likelihood problem. We're given a matrix H of size n minus k by n with entries from the field of size 2, that is, the matrix is binary. We also have a binary vector of size m and a non-negative integer w. The question is whether there exists a binary vector of size n with Hamming weight, which is the number of non-zero entries in a vector, less than or equal to w, such that when we multiply x by 8, we get y back. All problems in complexity theory are written in this yes or no form. Our claim here is that deciding this problem is NP-complete. The first step in proving that a problem is NP-complete is proving that it belongs to the set NP. Recall that a problem is in NP if we can verify its solution in polynomial time. For MLT, a solution is either a yes or a no. And in order to verify this, we need a certificate that claims to be a solution to the problem. A certificate for MLT is given by a vector of Hamming weight less than or equal to w. We can use this by simply multiplying it by 8 on the left and verifying if it equals y. Both of these steps can be completed in polynomial time as shown here. Now we need to prove that MLT is NP-hard. In order to do this, we need to show that all problems in NP can be reduced to MLT. But since reduction is transitive, if we can reduce an already NP-complete problem to MLT, then we're done. So the outline of the proof is to introduce a new problem called 3DM, assert that 3DM is NP-complete, and then reduce this problem to MLT. We define the three-dimensional matching problem as follows. We have a set T which is finite. We take the three-dimensional product of T given by T times T times T, or T3, and we're also given a subset U of this three-dimensional space. The question to be decided is whether there exists a subset of U called W, which has the same size as T, and no two elements of W agree in any coordinate. This problem was one of the original problems in Descartes' famous paper on NP-completeness. Here is an example for the 3DM problem. We take the set T equals 1, 2, 3, 4, and the subset U of size 6. On the left, both examples 1 and 2 consist of 6 ordered triples, all drawn from T3. On the right, we have an alternate representation of example 1 called an incidence matrix. The labels on the right of this matrix are simply members of U. Note that the columns are divided into 3 sections, each corresponding to one of the dimensions in T3. If we look at the first row, 1, 2, 1 simply means that the first section has 1 in the first column and 0 in the other 3 columns. For the second section, there is a 1 under 2, and similarly for the third section, we have a 1 under 1. Repeating this for all 6 elements gives us a binary matrix of size U times 3T. Now here's a crucial observation. If this instance has a solution, we need a subset U of size 4 such that no two elements agree on any coordinate. Here, agreeing on a coordinate implies that we have ones under the same number from T in some section. For instance, 121 and 132 agree on the first coordinate and so have a ones under 1 in the first section. Thus, a solution to a 3DM problem is the existence of T rows where the columns sum to 1 mod 2. Now, we'd be done if we can reduce 3DM to MLT. This means that we can solve 3DM in polynomial time if we have an algorithm to solve MLT in polynomial time. Using the input of 3DM as a subset U of T3, we construct an incidence matrix A of size U times 3T, and the input to the MLT problem is given by this matrix A, a vector Y of all ones, and W equaling the cardinality of T. If there exists a solution to this instance of the MLT problem, then there exists a vector X of Hamming weight T such that Xa equals Y, and this implies that there is a subset W of U with size T such that no elements of W agree, and our reduction is complete. We'll expand a bit more on this by viewing the matrix multiplication x times A as multiplying the columns of A by x to get ones. But x has Hamming weight T, that is, only T values of x are non-zeros, and thus we multiplied and added T entries in each column to get ones. Since this holds for all columns, we can guarantee the existence of T rows so that their mod sum equals a vector of ones. The by implications, along with the fact that all the steps can be computed in polynomial time, ensure that the reduction is valid.
I will quickly go over an application example of the hardness of decoding linear codes, the example being the Michaelis crypto system. The security of the Michaelis crypto system, which has been previously described, relies on there being no known decoding algorithm for a general linear code, despite there being an algorithm to solve general GAPA codes. This system appears quite secure while also allowing for rapid data rates. The Michaelis crypto system does not use the usual integer factoring problem or the discrete logarithm problem, which makes it more secure on the fact that the system relies on the hardness of decoding linear codes. No polynomial time algorithm has been found to reduce these problems. Also, quantum computers will easily solve RSA problems versus no quantum algorithm for Michaelis. So to summarize, throughout this project, we looked at the hardness of decoding linear codes. We tackled this problem by talking about the proof of this problem being NP-complete, three-dimensional matching and its application to the NP-hard proof, and applications to cryptography, with the application example being the Michaelis crypto system. Thank you for watching, and we really hope you enjoyed this video.